Yay!
Yay! Okay, let's do a simple example of what we're going to call an elastic collision. First of all, an elastic collision is one where the kinetic energy is conserved. So the initial amount of kinetic is the final amount of kinetic. And you might say, wait a minute, I thought always energy is conserved. But we're only talking about kinetic. For example, like if two cars crash together, all the kinetic energy of the cars is not conserved, right? If it's, for heaven forbid, a head-on crash, a lot of that energy goes into deforming the cars, right? It's not expressed as kinetic energy of motion after the crash. So this is a special kind of collision, and it's called elastic because it's the kind of thing that happens between, I don't know, like rubber balls or something like that, where there's no deformation. Things are pretty much the way they were beforehand. Billiard balls are roughly elastic. There's a little energy loss when they collide because they make a little clicky noise when they come together. But basically, if they're slow enough so you don't like fracture the balls or something, the energy that comes out after is about the same as it was before, the kinetic energy. So these are what are called elastic collisions. In nature, probably nothing is exactly elastic, but a lot of things can be approximately elastic. And so that's what we do, is we just say, well, this is approximately elastic. Not much energy is lost. Because, as you'll see, this enables us to get answers to problems that we wouldn't have been able to do otherwise. So it's a really useful approximation. Okay, let's see how to do it. First of all, we can use two principles now, right? If kinetic energy is conserved, that's one thing. And then if momentum is conserved, that's another principle that we can use. Okay, so here, for example, I have cart A, and cart A is going to hit cart B. Cart B is at rest. We'll do all of this with one of the carts being at rest beforehand. And then we'll come back to that and talk about that at the end. Okay, so if one cart hits the other and they just sort of bounce off of each other, the final condition, I have here A is like 2 kilograms and B is like 6 kilograms. The final condition, I'm going to suppose, is that A bounces backwards and B moves forwards. We'll see if that's right or not at the end. But notice that I've only got the initial speed. I don't know the speeds, the final speeds of either of the carts. I'm going to try to predict them. And the problem is this. If we tried to solve this just using conservation of momentum, I would have this. I would have MAVA initial plus MBVB initial, but we're saying that's 0. It's MAVA final plus MBVB final. Okay, that's conservation of momentum, right? The problem is, I don't know, I only know VA initial. I don't know the final speeds. I want to calculate those, but that's two unknowns in one equation, so that's not good. But if the kinetic energy is conserved, I can write down another equation. I can say this. I can say 1/2 MAVA initial squared plus 1/2 MAVA, oops. That's still 0, but I'm just writing it down for completeness. Is 1/2 MA, oops. Okay. So there's my kinetic energy equation. Now, I still don't know VA final or VB final, but the nice thing is that I have two equations and two unknowns. So with enough effort, I should be able to do it. By the way, all these halves go away. So that's nice. So the name of the game is to try to figure out what VA final and VB final are. Which is neat, right? Because I don't need to know either of the two final speeds. I'm going to try to predict them. So this is why this approximation is useful. I couldn't do this with just the conservation of momentum. Okay, so let's see what to do. How about this? What if I say, that VB final squared. Let me divide by MB. This is going to be MA over MB VA initial squared minus okay, it could be that, right? Just solving for VB final. Let's do a little trick. There's a way to do this using a quadratic equation and getting the roots and so on. But let's do a little trick. I can pull out that factor of MA over MB, right? And then I'll have VA squared, VA initial squared minus VA final squared. But look, isn't that the same thing as this? That's just this. VB final squared is MA over MB. One thing squared minus another thing squared, that's just this. It's just, oops, I don't know why I always want to write that first. That's just going to be VA initial. I think I'm going to write this one first, minus VA final, VA initial plus VA final. I can sort of factor it, right? Because when you multiply those things together, you get the thing that's above. And the reason I sort of want to do this is go back and look at this. What is VB final up here? It's if I divide by MB, VB final is, what would it be? It would be MA over MB, VA initial plus, minus, I'll just write it. It's this. Look, I've already got it right here. It's just this. That's just VB final from the momentum equation, right? If you divide by MB and then subtract the A final over to the other side, that's just VB final. So that equation already has one VB final right there. So maybe I can divide by it, right? I can sort of take the square root of both sides. So, and by the way, I can only do that if that thing is not 0. What would it mean if it were 0? If VA initial minus VA final is not 0. So as long as that's not 0, I can sort of divide by that. What if it were 0? That would mean that VA initial equals VA final, and that would be really weird, right? That would be the case where A just sort of floats right through B and doesn't even interact with it. The speed of A doesn't change. So I know it's going to change, so I'm safe in going ahead and factoring this out. So that means the thing that remains on the right-hand side over there, that must be also VB final. That means that VB final is equal to that thing. That's really interesting. Look at that. VA initial plus VA final. That's kind of, I'm going to box it. That's sort of a cool thing. It just says that the final velocity of B is what I get if I add together the initial and the final of A. That's sort of an interesting relationship. That's worth remembering as kind of a shortcut. Okay. Okay, so if I have that, let's see, what else am I going to do? So now let's solve for VA final. So let's look at this over here. I'm going to have VA final is just going to be, let me divide out by MA. So it's just going to be VA initial minus MB over MA times VB final. Well, I just found VB final, so that's going to be VA initial plus VA final. Okay. So I've got that. Now I can sort of collect the like terms. On the right-hand side, let's see, this is going to be 1 minus MB over MA. times VA initial. And the final over there is going to be a 1. If I collect the terms and then divide, I'm going to have a 1 plus MB over MA VA final. Okay. That's a little bit cumbersome to use. Let me go through, instead of a 1 on the top and the bottom, let's say that instead of that 1, let's use that as MA over MA, right? This is just going to become MA minus MB. In the denominator, I'm going to have MA plus MB times VA initial. There we go. So here's one expression. There's the final speed of A in terms of the initial speed of A. And that's what I want, right? Because the initial speed of A is the only thing that I know. So that's one thing. So now what I want is VBF. Oh, well, I've got that. VBF, the final speed of B, is just going to be this thing. It's just going to be VA final. So it's just going to be, it's VA initial with our little boxed equation up there, VA initial, plus the thing I found for VA final. So this is going to be MA minus MB over MA plus MB, VA initial. Neat. Well, I can add these together if I multiply by what my calculus teacher used to call a well-chosen 1. So that first term, let's multiply that times MA plus MB over MA plus MB. And so then the MAs add together and the MBs cancel each other out. So this is just going to be 2 MA over MA plus MB, VA initial. All right, there's my other one. Cool. So sure enough, we found the final velocities of the two carts in terms of the initial velocity of cart A, which is what we had. That's the only thing we knew. So that's it. That's the whole ball game. Okay, let's check it out. I think, oh yeah, I already got the masses up there, right? Let's see how this works. So with the masses that I have up there, VA final, what's that going to be? That's the difference of the masses. So 2 minus 6 divided by the sum of the masses, 2 plus 6. So that's going to be minus 4 over 8, or minus 1/2, times the initial speed, which was like 12. So the final velocity of A, sure enough, A is going backwards at a minus 6. And what about VB final? VB final is going to be twice MA, so that's going to be 4, divided by the sum of the masses, which was 8. So that's going to be plus 1/2 times VA initial. So that's a plus 6. And by the way, look how neat that works out. Our little boxed equation up at the top is the final velocity of B. Is it just the initial of A plus the final of A? Yeah. 12 plus a minus 6 is a plus 6. So it works. Neat. Okay, so that's how you find out the final velocities. It's always a good idea just to take a second and make sure that the two principles hold, just to satisfy yourself that this actually works. Let's go back and let's make sure that the conservation of momentum holds. Okay. Check. What is our check the momentum? Our initial momentum was, let's go back and see, 2 traveling at 12, right? So our initial momentum is 2 times 12 plus, and just for completeness, 6 times 0, right? That's going to be 0. Does this equal the final momentum? The final momentum is 2 times a minus 6 plus 6 times a plus 6. So what? This is going to be like 24. This is going to be minus 12 and 36. And sure enough, that checks out. So momentum was conserved. What about kinetic energy? Let's check our kinetic energy. This is going to be 1/2. Initially, it's going to be 1/2 times 2 times 12 squared, and then 0 for the other thing. Is this the same thing as 1/2 times 2 times minus 6 squared plus 1/2 times 6 times plus 6 squared? Let's see. This is going to be 144 on the left. On the right, what do we have? What's nice is that the 1/2 and the 2 cancel. So this is going to be 36 plus, let's see, 6 cubed. What is that? 216, and a half of that is 108. 108 plus 36. Yep, sure enough. So both of them hold. So that's just sort of a sanity check, right, to make sure that we didn't blow a sign somewhere. So momentum is conserved and kinetic energy is conserved. There's one other little thing that I wanted to check. Let me write down the relationships again. The relationship was VA final is MA minus MB over the sum of the masses, VA initial, and the other one was VB final is 2 MA over the sum of the masses, VA initial. Okay, here's something else to check, just to make sure that everything is all right. Let's see what happens in some limiting cases, and this is going to be really useful as we go on. Pretend this is like ping pong balls and bowling balls. Suppose that A is like a ping pong ball. So suppose that the mass of A is a whole bunch less than B. Suppose that's true. So it's like a ping pong ball hitting a bowling ball. So what happens in that case? We'll look at what happens VA final. If the mass of A is a whole bunch less, if MB is a whole bunch greater than MA, that fraction just pretty much turns into minus MB over plus MB, right? That's a -1. So this turns into VA final is just approximately minus VA initial. It just turns right around. Well, that's what you expect. If you throw a ping pong ball at a bowling ball, what's going to happen is the ping pong ball just turns right around with the same speed, right? Because kinetic energy is conserved, the same V. And what happens to B? VB final? Well, MA is a whole bunch less than MB, so that denominator dominates. And so this is pretty much 0. Okay, again, like we expect, you throw a ping pong ball at a bowling ball and the bowling ball doesn't move. What happens if they're equal? MA equals MB. If they're equal, look at that. VA final, oops. VA final is just 0. That's cool. So if there's two things colliding and they're equal masses, then one just makes the other go, and the first one comes to a stop. What about B? VB final. Let's see, if they're the same, that's just going to be 2 MA over MA plus MB, but they're the same mass, right? So that's just going to be it's just going to be a 2 over 2, or MB is MA. Yeah, it's just 1, just VAI. Yeah, that's what we expect. So one comes to a stop and the other one goes at the same speed if they're the same mass. Neat. Okay, what about this one? Suppose you reverse it. So now you throw a bowling ball at a ping pong ball. Well, then what's going to happen? Well, what happens to the bowling ball? If A is a whole bunch larger than B, you just pretty much get 1 VAI. You just get VAI. So pretty much the bowling ball just continues right on through, right? And that's what you expect to happen. What happens to the ping pong ball? Now, this is the interesting case. VB final, what happens to VB final? It's 2 MA over MA, right? MB doesn't really matter. And that's 2. It takes twice VAI. You pick up twice the speed of the bowling ball. Now that's maybe something that is new that you hadn't thought about before. So if a bowling ball hits a ping pong ball, If the bowling ball is going 10 meters per second, the ping pong ball is staying put. When they collide, the bowling ball doesn't really slow down. It still goes at 10, but the ping pong ball picks up 20, right? That's awfully interesting. That's gonna come back again when we solve some problems in the future, like the gravitational slingshot and the gravity assist, as well as some interesting things you can do with basketballs and tennis balls. So this is something that's maybe not obvious, but it's a really interesting effect. And then you can go back and verify that sure enough, VB final is the sum of the speeds of VA. That still works here too. Okay, so far we talked about the case where initially one of the carts is sitting still. We need to talk about the more general case because, I mean, maybe you think, how often does that happen? It turns out not often. Usually both things are in motion and they collide. So how do we handle the case where both things are moving? Well, that's what's next.